Hi, I'm Ed Marcus, and I'm a developer evangelist at Hedera. Now let's see how you can deploy a smart contract that works with other Hedera services, like the token service. So by the end of this video, you'll have a contract that can mint new tokens, associate Hedera accounts with tokens, and transfer a token between accounts. If you want to try this code right away, I set up this example for you in Code Sandbox. So all you have to do is click the link below, fork the sandbox, enter your testnet account credentials, and then you'll be running this example in no time. Now, in the last video, you saw that you deploy smart contracts on Hedera in 4 steps, where you write the contract in Solidity and compile it into bytecode. You add the bytecode file to Hedera, then create the smart contract on Hedera, and call it or query it to interact with it. Let's start by looking at the contract in Solidity. To keep this video short, we'll walk through the Solidity code, and we'll do most of the actual coding with the Hedera SDK. But if you want to see how to get a testnet account, set up your development environment, and write and compile a simple contract, then check out the last video where I go over all of that in more detail. So if we look at this smart contract, it starts with the typical license and pragma statements. It also imports 2 other files, which include precompiled contracts that enable us to work with Hedera tokens. And these files have to be present in your directory. In this case, they are in this folder here. And there's also a 3rd file that has to be present because it supports the 2 files that you import. And you can get these files from this GitHub repository, and there's a link included in the description below. So now we see that our contract is called mint_asso_trans, HTS, and we're using is to derive from this other contract that we're importing. The first thing that we do is create a state variable of type address, and that is the token address that we're going to pass to our contract through our constructor when we first create the contract. So you see there that value is being set to whatever we pass through the constructor. And then we have 3 functions in our contract that will serve to mint, associate, and transfer tokens. So if we look at mint fungible token, we see that this function takes a uint64, that is the amount of tokens that we want to mint, and then this function uses that precompiled contract that we imported. In fact, it's accessing the mint function, the mint token function in that contract. And what you see here is that this mint token function takes a token address, an amount of tokens that we want to mint, and if you're working with NFTs, then you would pass some metadata. In this case, we're minting a fungible token, so we're not passing any metadata. And if you want to confirm the inputs and outputs of the function in that contract, then you can easily inspect that by going to that file. This function, mint token, and again, these are the inputs that we're passing, which are the token address, an amount, or the number of tokens we want to mint, and the metadata that we want to pass if we're working with NFTs. So that's how you can confirm the inputs and outputs that your function will work with. So in this case, as the outputs, we're capturing a response, a new total supply, and the serial numbers in case we're working with NFTs, which doesn't apply in this case. And if the response is not successful, then we pass a failure message. In this case, we're not going to be using these outputs very much, so we can move on quickly to our next 2 functions. And the workflow here is the same, right? We have token associate, which exists in that other contract that we imported, and here we specify the account that we want to associate with our token. So remember that our token is the state variable, and the account is what we would pass when we call this function. We also log the response or capture the response and then output a failure message if that response is not successful. And finally, we have the token transfer function, which takes as input the sender address, the receiver address, and the amount of tokens that we want to transfer as an int64. And this function comes from the Hedera Token Service contract. We use the transfer token function. And again, these are the 4 things that we would pass to the function. There's also auto response and the failure message if that response is not successful. So with that quick walkthrough of the contract, once you are ready to compile the contract, you can just go to the terminal and type the command solcjs, define the output as binary, and then you would take your contract file and you would specify it with this solcjs command to compile it into bytecode. In this case, we already have the bytecode, so we'll skip this step. Just wanted to show you that. And now we can take a look at our index.js file. Here I want to remind you that we're using Visual Studio Code with the JavaScript SDK. And Hedera also has SDKs for Java, Go, and community authored and supported SDK for Python and .NET. So in this JavaScript file, we start with this clear statement to clean up the console. Then we require and configure the .env package, which allows us to work with the environment variables. And here are modules that we import from the Hashgraph SDK. These are the ones that we're going to be using today. We're also going to need the node file system module, so we require that here. And here we configure the operator, treasury, and Alice's accounts. And all these testnet credentials are coming from the .env files where we entered those testnet credentials. We also configure the client. We do that with the client module. We configure it for the testnet and set the operator to the operator ID credentials. So here's the ID and the key. And we can configure the maximum amount of HBAR that we want to pay for transactions and queries. So we could do this at the client level or at the request level. And here I have detailed the steps that we're going to follow. We'll do this in 4 steps. And here at the bottom, I also want to show you some helper functions that I wrote to do simple things like token information queries and account balance queries. We're going to be doing that a few times to confirm that our code is working. And we can start now with the first step. We're going to start by reading the contents of the binary file that contains the bytecode, and then we're going to store that in this bytecode variable. So we'll use the node file system here with this read file sync. And then what we'll use here is we'll point this to the binary file that we have in our working directory. So we'll grab that from here. And that is all there is to the first step. So then we'll just output a console message confirmation that this first step is complete. For the second step, we create a file on Hedera that stores the bytecode, but first we're going to create a fungible token given that our contract is going to manage the supply for that token. So we do that using the token service, and here we create this token create transaction variable. This uses await new because we're doing these operations asynchronously. And here we use the token create transaction module. We set a few properties for our token, like the token name. In this case, we'll go with something like HBAR rocks. We also set the token symbol. We'll use HROC for that. We also set the decimals for our token. In this case, we can work with no decimals. We set the initial supply to be 100 tokens. We also set the treasury account ID to be the treasury ID. And in this case, we want our token to be mutable, so we'll set an admin key for that token. And in previous videos, we've covered that if a token doesn't have an admin key, then it's immutable. You cannot update or delete that token. So in this case, we want the treasury to be the key or the admin key for this token. And initially, we'll also set the supply key to be the treasury. So with all these properties, we freeze this transaction with the client to get it ready for signing. And in this case, the transaction has to be signed by the Treasury account ID. And now we are ready to submit this transaction to the network. So we create this new variable token create submit, which is this signed transaction, and we use the execute method to submit it to the network, and the Hedera client that we configured does that for us. Then from that transaction, we can get a receipt, and it's the transaction that we created in the previous line, and we use the get receipt method, and that is also obtained by the client. From that receipt, we can also get some information about the token that we just created. In this case, we can get the token ID from the receipt. And we can also display that token ID as a Solidity address. So in this case, we'll use this variable token address sol. And the way to do that is with this toSolidity address method. So now we can output these two values to the terminal, and we can have a nice message with that says token ID is just that token ID that we obtained. And the token ID in Solidity format is this token address sol variable. Now we can do our first token query, and that will help us confirm a few properties of our token. So in this case, we may want to query the total supply for our token. So we'll just use one of those helper functions that we saw in the beginning. And that function, that helper function, was called tQuery FCN, and we just pass the token ID for that function. And so this variable will contain some information. For example, we can look at the total supply and obtain the number that is in there, and we can log that to the console with a nice message that says that the initial token supply is whatever is contained in that value. Now that our token is taken care of, then it's time to create that file on the Hedera network that contains the bytecode. So we'll create this variable for this transaction, file create tx, and this will use the file create transaction module. So one thing we'll do is we'll set the keys for our file. So these are the keys that will manage our file on the network, whether if it needs to be updated or deleted. In this case, let's assign this to be the treasury key. And let's set the content of our file to be the bytecode that we had from the first step. So now we can freeze this transaction with the client, and we can sign this transaction with the respective keys. So the key that has to sign is the one that we assigned in the previous line, and that would be the treasury key. And now we can submit this signed transaction which is the previous variable with the execute method, and that is done by the client. And then just like the previous step for the token, we can now get a receipt for our file. So file create receipt is a transaction that we submit with the get receipt method, and that's obtained by the client. And from that receipt, we can get more information like the bytecode file ID, which we'll store in this variable. And finally, we can output that bytecode file ID to the console with a nice confirmation message. So here we could say the smart contract bytecode file ID is whatever is returned to us from that variable. Now, I want to try to run this, and I know this is going to error out, but there's something important that I want to show you here. So if we execute our index.js, you will see that in this second step, when we try to create this file, we get an error that says transaction oversize. And right now, the file that we're trying to append, the actual bytecode file, is too large to be able to submit it in one single transaction. So what we have to do is we have to create an empty file first and then append the content for that file with a file append transaction. So let's see how you can do that in the next step. Here is where we append the contents to the file. And we'll start with this variable file append tx, which is a new file append transaction module. And some of the properties that we have to set here is the file ID, which would be the bytecode file ID variable that we have from before. That's the file that we want to append the contents to, and the contents that we want to append is the bytecode. And the next thing that we want to do is specify the number of max chunks. And this is what chunks up the file so that it can be handled by individual transactions. Every transaction in Hedera is limited to 6 kilobytes, and the bytecode file is greater than that limit. So that's why we need to chunk it up to be able to append it to the network. In this case, 10 would work. We can now freeze this transaction for signing with the client. Now we can file append sign, which is this previous transaction with the sign method, and it is the treasury key that needs to sign this operation here. Now we can submit. Which is the sign transaction with the execute method. That's done by the client. And the last step, as you know by now, is to get the receipt. So file append rx is this submit transaction with the get receipt method. So now we can output a confirmation message to show that this operation was successful. And we can say that the content was added. And now we can verify that by going back to the terminal and trying to run this again. Excellent. So here is the file ID of the empty file that we created, and then here's the confirmation message saying that the contents for that file were successfully appended. So now we can move on to the third step, and here we want to create the smart contract on the Hedera network. So we'll do that in this variable contract instantiate tx. This is just a new contract create transaction. The first thing we'll set here is the bytecode file ID. And that's this variable bytecode file ID. We'll set the gas to something really high to make sure our transaction succeeds. Now remember, this is the testnet, and with Hedera, this gas cost is relatively low compared to other networks. I encourage you to check out the documentation and read more to understand all the fundamentals and core concepts associated with gas on Hedera. From memory here, I believe there's a 4 million gas limit per request on Hedera, and we're below that limit, so we should be okay here. The next thing we set is the constructor parameters, and here we use the contract function parameters module. And if you remember from looking at our smart contract, our constructor requires the address of the token that we'll be working with. So we'll add that address. That is the token address in Solidity format. So now we can submit that transaction. We'll take the transaction from the previous step and use the execute method with the client. And from that, we can get now a receipt, which is the transaction that we submit. And we also use the get receipt method. So from that receipt, now we can get the contract ID. And at the same time, we can also get the contract address from that ID. So we'll just call that contract address, which is the ID. And we simply use the Solidity or toSolidity address method to do that conversion for us. So now we can log these two pieces of information to the console. And here we can say that the smart contract ID is the value in that variable. And here the smart contract ID in Solidity format is that. Now that we have our HTS token and our contract instantiated on Hedera, it's time to update our token properties so that the supply key for that token is this smart contract. In other words, that is what enables the smart contract to manage the supply for the token. So let's start by doing a token query to confirm the token supply key initially. We're going to call this token query token info 2.1. And for that, we'll use our helper function that we used before. We'll pass it the token ID. And the next step would be to log to the console the supply key that we get from that query. So that's supply key, and we want to log that as a string. We can add a nice message to that, which says that the token supply key is what we get in return. And from that, now we can proceed to update the fungible token so the smart contract manages the supply. So we'll do this with a token update transaction. There is the module, and then the first thing that we specify is the token ID that we want to update. Then we set the new supply key that we want to pass, and in this case we simply pass the contract ID. Then we freeze our transaction with the client to get it ready for signing, and for this transaction we can sign it right in the same transaction, and the signature required is the treasury key, so we sign with that. And now we can submit this transaction. So the submit transaction is token update tx dot execute. Do that with the client. And as you know by now, the next step is to get a receipt. We do that with the client. And now we can update a status message to confirm that our update operation or update transaction went through successfully. So the token update status will be the status of the transaction. All right, and now we can do another token query. I'm just going to reuse some of the code that we have from above. And we'll call this one token info 2.2. And this will help us verify that the contract will be the new supply key for our token. So before we get to step 4, let's run our code and confirm. Excellent. So all the steps are completing as we expect up to this point. And the last thing that we did in step 3 was to create the contract. Here's the contract ID. Here's the contract ID in Solidity format. Here was the initial supply key. So this was the treasury, right? When the treasury was managing the supply for our token, then we updated our token. And now the supply for the token is managed by the contract. So now if we go back to our code, we can proceed with step 4. And in step 4, we're simply going to execute the contract functions. We'll start with the mint function. And so we'll create this variable contract exec_tx. And this will use the contract execute transaction module. We'll set the contract ID, also set the gas. And again, I'm going to use a really high value of 3 million. And this is another reminder to go read the documentation about how gas works on the Hedera network. Now we'll set the function. In this case, if you remember from our contract, we want to call the mint fungible token function. And we can take a look as a reminder to see the inputs that that function requires. So in this case, we only have to pass an amount when we call the mint fungible token function, and then the rest is taken care of inside the function itself. So now we pass the contract function parameters, and here we'll add a uint 64. And let's say we want to add 150 tokens to the existing supply. If you remember, the initial supply was 100 tokens, and now we're minting 150. So now we can submit that, and for that we're going to have this variable contract exec submit. And for that we'll use the execute method. And now we can get a receipt. From the transaction that we submit with the get receipt method. So let's correct this here. And now we can log to the console the status of this operation. So that'll tell us if the mint operation was successful or not. And then we'll do another query. We'll call this one token query 3. So we'll just reuse some of this code. We'll call this variable token info 3. And now here what we want to verify is that the new token supply is obtained from token info 3, and here we simply get total supply. Excellent. Moving on, we have 2 more functions in our contract to execute. And we'll do that. We'll execute this associate transaction by simply reusing some of this code that we just wrote for the first function. One thing that we'll do is we'll add a few ones here to the name of these variables. And we also have to change a few things for the actual function that we're calling. So in this case, we're calling token associate. And this actually takes an address. In this case, we'll pass Alice ID, and we'll convert that to a Solidity address. One thing we have to do here is we'll freeze this transaction for signing. And in this case, this transaction actually has to be signed by Alice. She has to authorize her account being associated to this token. So contract exec sign is this transaction with the sign method, and we sign using Alice key. And then we have to submit the signed transaction. Excellent. So now we can output to the console a confirmation message that gives us the status of this operation. And we can add a message to that that says token association with Alice's account. And now the last step is to execute the transfer transaction. So we'll do the same thing we just did. We'll reuse some of this code and we'll renumber these transactions. Now that that's done, we need to change the function that we're going to call. In this case, it's token transfer. And if you remember, this function takes 3 inputs. The first one is the address of the sender. In this case, it's going to be the treasury. The second one is the address of the receiver, which is Alice, so we can leave that here. And the third one is the number of tokens that we want to send. So let's simply add an address, and in this case, this will be the treasury ID in Solidity format. And the third thing we'll add is an int 64, which is the number of tokens that the treasury will send Alice. In this case, we can send 50 tokens. So now we can freeze that with the client for signing. And in this case, since we're deducting a balance from the treasury has to sign this transaction. So after signing, we submit to the network with the client, and then we get a receipt for this transaction. Then the next step would be to output to the console the status of the token transfer. We can get the status of that transaction from the receipt. And finally, the last thing that we want to do is we want to check the account balances for the treasury and for Alice. So for that, we're going to use the helper functions, one of the helper functions that we wrote. In this case, we'll use bchecker function. We'll just pass treasury ID. And we'll do the same thing for Alice. So here we pass Alice's ID. Now we can output to the console the first message that would say treasury balance is whatever number is in there, and we can add to our message this text here, units of token, and then we can also pass the token ID to have a more complete text. Then we do the same thing for Alice. And that'll show us Alice's balance for our token. With that, it's time to test our code and rerun. So we bring back the console or the terminal, and we execute our code. Excellent. So in step one, the first thing we did was to read the content of the binary file, which is the compiled bytecode from our contract, and store that in a variable that we could use. In step two, we created our token. Here is the token ID. Here's that token ID in Solidity format. And we started with 100 tokens as the initial supply for our token. We then created a file on the Hedera network. Here's the file ID for that, and we added our compiled bytecode as content for that file. Then in step three, we instantiated our smart contract. We created our smart contract on Hedera. Here's the ID for that contract. Here it is in Solidity format. Then we started by inspecting the supply key for our token before updating the token. Then we did an update, and with that update, the contract is now managing the supply for the token that we created. And then the last thing that we did in step four was to call contract functions. So the first thing that we did was call the mint function. Here you see the success status of that transaction. Here we queried the total supply for our token. So it went from 100 to 250. So the 150 that we minted were successfully added to that supply. We then associated the token with Alice's account and then transferred 50 tokens from the treasury to Alice. And so here is the status for that transfer. And here we can check that the treasury has a balance of 200 tokens and Alice has a balance of 50 tokens. So that is our example of a smart contract that works with other Hedera services like the token service. If you're interested in a written guide of the example that we just worked on, I encourage you to find this article in the Hedera blog center. It has important links to resources you'll find helpful, documentation, and a little bit more background on each one of the operations and steps that we took today. It also has links to this code in GitHub. So here's where you can access the code if you want to fork it and start modifying it to your own purposes. And I also encourage you to check out the documentation. There are excellent examples that will help you get started with the Hedera Token Service, with smart contracts, and a lot more. And the documentation also has great information on how smart contracts work on the Hedera network. That includes gas and fees, so that's important to understand. Lastly, you can keep learning in the Hedera Learning Center, from topics about the distributed ledger technology space, topics about Hedera, and even cryptocurrencies. And I also want to invite you to join the Hedera Developer Discord. And here are many technical discussions happening regarding all the Hedera services and a lot more. So with that, I will see you in Discord and I will see you in the next video. Thanks.